There we go. Is that going? Yes. And I think I want this one full screen. Is that right? Yeah. Okay, cool. So we're going to start by talking about propositional equivalence, which is really just like showing that two propositions are actually the same thing logically if you break them down. What I want to introduce a bit here is some of the sort of comparisons between this and computer science, between what we're doing in this class and computer science. So to begin, I guess I'm assuming everybody here has done like a intro to some programming language course, right? Whether it's like high school or first year university or wherever, right? Where it's like, okay, here's a rundown on like Python or Java or whatever, right? So what's the way that those courses tend to work, I'm sure you know, is like first you introduce like variables, right? Usually you start off with like, here's how you declare variables and here's how you print stuff, right? And then you move on to like if statements, usually, right? You'll do if statements, and then eventually maybe you move on to like functions, right? And so like, in a sense, and sorry, after that you might move on to like while statements and for loops, right? And so you're sort of like building and building and building. That's what we're doing in this course. So the first thing that we did last week was propositions. Those are like variables, right? We introduced these propositions, which is what we're calling variables. We showed how they interact with each other, different operations you can perform on them. Now we're doing propositional equivalence, which is kind of like if statements. So it's like comparing two different combinations of these variables, right? Predicates are like functions. That's literally all they are. Anytime you see the word predicate, you can change it for function. It's the same thing. And then quantifiers are like, in a sense, they're similar to like while loops, or like they're like, you know, how often something's repeating, right? So really, although we're using different words because it's math, right? This is very similar to learning a new programming language. So sort of treat it like that. Okay, so we're going to start off with propositional equivalence. Kind of want to do a rundown. So last week we talked about, we did a truth table, and I think the thing here that we did was this. Does everyone kind of vaguely remember that? Us doing that truth table? Cool. So that truth table, I think we started off with P, and it was true, true, false, false. And then we had Q, which was true, false, true, false. So this gave us like every combination of P and Q, where one's true, one's false, that kind of thing. We did a bunch of work, and then eventually we got to the end result, and you can look back on your notes, but it came out to be this: true, false, false, true. Great. Now, you know, maybe at first glance, you know, that doesn't really mean anything to you, but if you look back on your notes, you should see a truth table for not P, sorry, P bijection with Q, or biconditional with Q. And I believe it was the exact same, right? It's like an if and only if. You guys remember that one? Yeah? So the end result of this was the same as this, which means that these two are identical. Does that make sense? If you were, you know, also keen, you might have noticed that this is the opposite of P XOR Q, right? The negation of P XOR Q. So this is the same thing as the negation of P XOR Q. So why is this important? Why do we care? Well, because if you're writing code, right, you want things to be as efficient as possible, right? You don't want like a bunch of crazy stuff going on. So if your logic worked out, like in your head, worked out to something like this, and then you were able to change it into something simpler like one of these two, you're saving all those computations, right? So why not, right? That's why we're doing this. In your code, you should use that. You should not use this, right? Especially if you want it to run fast. So that's one way to do equivalence. Another way to do equivalence is using identities. So we have a list of identities. I think it's in lecture 2, whatever the lecture we did propositional equivalence in. It's in that lecture. So you have a table of different identities. Probably one of the, a lot of them make sense, I think. Like you can move propositions around. You can, that's called commutativity. You can re-bracket things however you want. You can distribute things over brackets, right? Or like factor something out. Double negation, right? It's sort of like, a lot of those make sense. I think the one that tricks a lot of people up is De Morgan's law, which he has 2 of them. Not P and not Q. So what we do is we can distribute, all De Morgan's laws is we can distribute a negation over brackets, but when we do so, we have to flip the or to an and or an to an or. Does that make sense? So let's say that P is that you have a dog, and that Q is you have a cat. So this statement here says it's not true that I have a dog or a cat. So I don't have a dog or a cat, right? That's the same thing as saying I don't have a dog and I don't have a cat, right? So although it may seem weird when you're like doing it, it might not seem natural to have to flip the sign or flip the or to an and. It actually is, and in the real world, you actually do that, right? You do flip the or to an and. Does that make sense? Cool. Okay, one more is the implication. So if you ever see an implication or a conditional arrow, those can be hard to deal with in proofs sometimes, like in writing them out. Even like if you're thinking like an if statement, right? If you were writing like some sort of logic in your code, you don't really have like a conditional operator, right? Not at least directly, in the same way that like, in Python, for example, you have like an or operator and a not and an and, right? And maybe an XOR. But you don't really have a conditional. That's not really a thing. Well, the conditional is the same thing as not P or Q. And I'll let you sort of double check that, but that's a way you can simplify it, both in proof and in code. And like I said earlier, the biconditional is the same thing as not of PX or Q in brackets. Any questions about propositional equivalence before we move on? All good? All right, so maybe I'll do it over here. Okay, so now let's talk about predicates and quantifiers. So as a show of hands, has anybody in here not taken calculus? No? Okay, good. So everyone in here is taking calculus. I'm going to define a variable or a proposition x, and this is going to represent a person in the class. Okay? Then I'm going to define a function, which I'm going to call c of x. Just a function. This is going to be a function related to calculus. So it's a function, it's going to take in a person in the class. It's going to spit out true if that person has taken calculus, and it's going to spit out false if the person has not taken calculus. Sound good? How many people in here have taken linear algebra? Good, so a couple people have taken linear algebra. So I'm going to do the same thing with L of x, where L means the student's taken linear algebra. Cool. And any people in here taking real analysis? No? Good, so I'm the only one. We're going to say R of x is real analysis. Cool. So we have 3 functions. Each of them returns true if the person you plug in has attended that class or has taken that class. Everyone in here has taken calculus, right? So we can write for every x, for every person in this class, C of x is true, right? And just like in Python, if you have like a Boolean value, you don't have to write like equals true, right? If you just say if that Boolean value, we're good, right? So it's the same thing here. You don't have to write like equals true. But for all x, if we know C of x is true, right? For every person in this class, we've all taken calculus. We can do something similar for linear algebra. So with linear algebra, there's some people who have taken linear algebra in this class. Anyone know what quantifier that means? Any ideas? Yeah.
There exists.
There exists. So there exists an x. We use this upside down A for every x, and we use this sideways E for there exists. And some words you might see associated here with the for every x, you might see like all or every, right? So if you see those words in like a English sentence, that usually means you're talking about for all. And if you see the words like some, something like that, usually that means there exists. Because people don't actually say like, like I was saying, some people in this class have taken linear algebra. That's the natural way to say it. You wouldn't actually say like, there exists a student in this class who has taken linear algebra, right? That's not, people don't talk about it. There's one more, which is there exists a unique x. So that means exactly one person, one x, who has taken real analysis. So again, you're seeing like words like one. Does that make sense? Cool. And again, C, L, and R, they're functions, we just call them predicates. Just the word we use. Any questions about anything we've done? No? All right, in that case, I'm going to stop the recording, if I can. There.